Okay, morning, everyone. Hello, I'm Yuxiang, a fifth-year PhD student at EC department, and I'm also a NSF ARVR PhD fellow. Thank you all for joining us this evening for the Voices of XR with Anurag Kumar. This series is made possible by Kathy McMurray and the National Science Foundation as part of the interdisciplinary graduate training in science, technology, and applications of augmented and virtual reality at University of Rochester. I would like to thank Anurag Kumar for joining us today. Dr. Kumar is a research scientist and technical research lead at Meta Reality Labs Research. For me, I personally was fortunate to have the opportunity to work there as a research intern. Although not working directly with Dr. Kumar's team, I surely witnessed their exceptional research and projects from his team. Specifically, his primary research interests are in the machine learning for audio and speech processing and audiovisual learning. He focuses on improving the perceptual quality and intelligibility of speech signals, for which is critical for improving communications in the real and virtual world, whether someone has normal hearing or some form of hearing impairment. So today he will discuss some of his recent research on both methods to enhance degraded speech, as well as methods for speech assessment. And he will go in depth on his recent works on unsupervised and self-supervised approaches for speech enhancement and how speech signals from the wild, for which target signals are not available, might be used for enhancement. Dr. Kumar has been the recipient of several awards and recognitions, including the Best Paper finalist at CVPR 2022 and NCC 2014, finalist in Qualcomm Innovation Fellowship 2017, winner of the Samsung Innovation Awards 2012, and travel grants from IEEE, SBS, and ERASIP. Well, that's a long list of awards. So everyone, please feel free to post your questions in the chat of this Zoom meeting, and we will have a Q&A session. And lastly, this session is being recorded and will be available to you later on the Studio X website. With that, enough of me talking, I'll turn it over to Dr. Kumar. The stage is yours.
Thanks, Yushing, for the introduction. It's good, glad to be here, and welcome everyone to my talk. First of all, thank you also, Chen Liang, for hosting me. Let's start. Yeah, so Yushing already gave an introduction, but just to complete it from my end, I'm a research scientist at Meta Reality Labs Research. Mostly I work on problems at the intersection of deep learning, machine learning, audio speech processing, and multimodal learning. Before that, I did my PhD from CMU, where my thesis was on actually acoustic intelligence or sound understanding. And my tiny bit of claim to fame is introducing weakly labeled learning for sounds. And even before that, I was an undergrad in India doing electrical engineering. Okay, so jumping on to what I'm going to talk about today, I guess most of the people here are familiar with augmented and virtual reality, especially this room and this space. You have all probably heard of different Meta virtual and augmented reality products coming, which are already out or which will be coming in future, Quest Pro, Ray-Ban Stories. Of course, here I'm going to talk about the research in this domain. And the research in this domain is often driven by egocentric learning, where you have the first-person view of either of the environment around you, the people around you. And by the way, to enable that, there is also another meta classes, which is available primarily for even for academic research. It's called Project Area, and where people have been using it to collect data and do really some really interesting research. So how does audio, what does audio and speech in AR VR mean? So the problems which come under which are defined by audio and speech in AR and VR are primarily enabled by these devices themselves. And these devices are a different type of device, are different from what we currently mostly use, like phones or tablets or laptops. They provide a different type of user experience, a different type of way you interact with them, and which leads to some old problems and some new problems. So, for example, these devices are meant to give you immersive environment, which would mean that you need to synthesize realistic acoustic environment or realistic sounds. They can be used for real-time communications and doing a lot of everyday activities, including work. So the generated sounds has to be, so perception becomes important. So the audio and the sounds are consumed directly rather than say a ASR or any other such system where it's like an implicitly audio is consumed. So perception becomes important. So overall, it introduces some there are some old problems, some of one of which I will talk about with a new type of new challenges, and then it also introduces some new problems. My research work, broadly, I can say that it comes under audiovisual scene understanding and synthesis. That includes things like sound event detection, localization, speech enhancement, separation, multi-channel and audiovisual versions of it, synthesis of these different type of audiovisual scenes. Just to mention a few. So a few things. I mean, like, I'm not going to list all the stuff which we have been doing. You can check that out later. But just wanted to highlight one which we have this active collaboration going on with Professor Chen Ling here, where we are working on both egocentric audiovisual scene understanding, where we're looking into how to analyze audiovisual scenes, especially in egocentric domain. It introduces new challenges like ego motions, and you have audio capture from moving headphones and so on, moving microphones, sorry. And then we are also looking into egocentric audiovisual scene synthesis, like how do you generate realistic sounding scenes in both audio domain as well as visual domain. You can check out these papers, they're probably already out. Today, I'm going to talk about this other problem which I am heavily invested in, which is enabling communication in really noisy conditions. So imagine yourself wearing AR glasses, and you are sitting in some noisy restaurant or cafe, and we all know how difficult it is to actually talk in those conditions. In a noisy bar or something like that. So in those conditions, but if you can imagine wearing your AR glasses, and you have effortless communication where you are talking to the right person. You can zone out the right amount of noise. You can keep some so that it lets you keep the acoustic scene. Your mind can still keep the acoustic scene in context, but at the same time the communication becomes much more efficient. So which brings us to the actual problem, speech enhancement and speech assessment, which I'll be talking about today. So at a very high level, the goal of speech enhancement is to improve quality and intelligibility of a degraded speech signal. And speech assessment is about how to measure, since we are aiming to improve the speech enhancement and improve the quality and intelligibility, how do we measure this quality and intelligibility in the first place? So these are the two high-level topics I will touch upon today. Before I go deeper, maybe I just want to do a call out to some of the people the work which is obviously involving a lot of my really amazing interns and also collaborators in my team. This is like roughly some of the papers which this talk touches upon, but you can just wanted to list them out in case you want to check it out later. All right, so let's jump into speech enhancement. I'll try to go into some of the parts a bit faster and slow down at some of the places which I think should require more time. But feel free to stop me, ask me any questions. I happy to answer question at any time. So speech enhancement, like I said, the basic goal is to improve the quality of and intelligibility of a speech. And obviously, it's a no-brainer that right now, most of it is driven by, and state of the art is driven by deep learning. So a typical training framework for speech enhancement will look something like this. You have a clean speech database, you have a noise database, you mix them in different ways, you essentially degrade the speech signal, you figure out some network architecture, and then you have the target, then you compute a loss based on the target clean speech, and you backpropagate and train. And then obviously there could be a lot of things in the network architecture, or what type of loss it is, whether it's time domain, time frequency domain, whether it's mask or complex ratio, mask-based approach, or directly trying to predict the output. Lots of varieties in here, but this is how a typical speech enhancement system looks like. The speech enhancement training looks like. Before going further, just a quick call out to something which probably everyone in this room already knows: supervised learning. There you have a database, you have labels for it, and to train a neural network, you use the labels, compute a loss, and train your network using that. And self-supervised learning, again, this has now become pretty popular, and like a lot of state of the art is achieved through self-supervised learning. Here you don't have labels, so what you have is essentially a large database. You have a network, and what you do is you create some sort of task using the data itself. That could be something like maybe taking part of the data sample and predicting another part of it, or a whole bunch of approaches. Like there are gazillion papers on self-supervised learning in every domain, for NLP, for image and speech. And then that's how you try to train the network, and to actually use this pre-trained network for another task, you essentially follow the same supervised learning approach. You take this pre-trained network and follow the supervised learning approach. So what exactly does, when I say reference-free learning, which is kind of an unsupervised learning for speech enhancement, what does it mean? So as I mentioned, if you look at this speech enhancement training system, it's almost like essentially it's unsupervised. You're not using much of human labels here, right? So what exactly do I mean when I say self-supervised learning and speech enhancement? Well, the first thing it could mean is basically you are using this similar to, like what I just showed about uses of SSL. You want to use the pre-trained SSL for speech enhancement. You can basically use the output from it to train a model. That has been shown to be pretty useful for, say, for example, automatic speech recognition, especially for, say, low resource conditions. Now, if you see, most of the speech enhancement are trained on this synthetic noisy clean pairs, right? So you have the noisy speech, you have the clean speech, and essentially which means you need the clean and noisy sample. So a different thing for as a speech enhancement in terms of SSL could also mean that how do we train without the target clean speech? So if we have a just noisy speech collected from the wild, can we train? Can we try to learn a network which learns from just this noisy speech without the target?
Hey, can I ask, are your noisy clean pairs, is it recorded at the same time and then cleaned, or is the noise added artificially to a clean audio?
Usually you just take any data sets, they could be collected at any time, it doesn't matter.
So presumably you have some clean speech and some noisy speech.
No, it's noise.
Oh, so, it's noise. So
yes.
It's just artificial noise? No.
Yeah, it's noise. It could be like whatever, any noise anywhere.
So you pair a clean audio with a random noise? Okay.
Yeah.
Okay.
So basically what you are trying to do is
I thought you had clean audio and noisy audio, and there was speech in.
That's what so when you're training a neural network, you need the target signal. So the way to do it is you take clean speech, you take noise, you mix the noise in the clean speech, and you create the noisy speech. That's synthetically decided. Now you have the noisy speech as input, and the target clean
Okay,
speech
yeah.
could serve as the target output.
Thank you.
So what here we are looking into is, can we train with just noisy speech, where we don't have the target? Because in real world, if you say, for example, if you're in your home and you collect some speech, there could be all kind of sounds and with the speech. So you'll have the noisy speech, but you won't have the clean speech, target speech. So how do we train with that and that type of data? So this could also be useful for adapting to an unseen environment. Like how do we can go into an environment, we can get some noisy speech from that environment and then do some sort of on the fly adaptation. So coming to the first part, and this is something which I'll go a bit quickly. There has been a few works on using on the first part, which is using pre-trained self-supervised learned models for enhancements. So the process is same as what you'd see in any self-supervised learning work. You first take the pre-trained SSL model, you use the output from it to train your speech enhancement network. The key thing, the main thing I want to just highlight is that when you do that, your overall speech enhancement system is basically now the union of the SSL model and the speech enhancement network. So irrespective of how you design your speech enhancement network, where maybe it could, you wanted it to be causal, you wanted it to be real time, all of that is gone, because now your overall system is this big SSL, with this SSL model, which are usually very large, usually very usually causal, and they're very far from real time. So we did some study on putting some constraints so that we want to use the SSL representation to do speech enhancement, but we want to retain the original speech enhancement network's characteristic. That is, which essentially means that the SSL representation should not be required during inference time. And if our original network is say causal, it remains causal. If it's small, it remains small. And we came up with like a whole bunch of, tried a whole bunch of approaches, some based on what already existed in literature, some of our own. And to summarize, nothing really gives a very big improvement, especially under those constraints that SSL representations need not be needed during inference. Distilling knowledge from actually, at least from speech SSL model, is not that easy. So for example, if you just take any large self-supervised learned models, which have been trained with, say, some sort of the popular ones, if you know about speech SSL, it's like Web2Vec, Hubert, and just try to train another architecture from scratch, which predicts those outputs, that itself turns out to be a very tricky task. It's still an interesting open problem on how can we distill, how can we use these SSL representations from speech SSL representations for enhancement tasks in particular. So in our paper, which is currently under submission, we show how what are the structure of the SSL representations and why knowledge distillation is a bit tricky thing to do there. The talk today will focus on this other way of thinking about speech enhancement in terms of self-supervised learning, where we want to train our speech enhancement model when target clean speech is not available. So that we can have train from any noisy speech without requirement of noise domain. So the big question obviously is, if you're trying to do that, you have the noisy speech as input. How do we compute the loss? What will be our loss? How will we train the network, right? So the basic idea is that we need some sort of reference to create a loss function with which we can train the neural network. That could be either in the latent space, that could directly be in the audio space. And in this talk, I'll present two work. Each one of the first one will be trying to come up with use this reference, this pseudo reference in the latent space, and the other one which will be creating a reference in the audio space and then using that. And the common thread between both of them is that in a way they are both kind of a source separation model. So you first try to learn to do some sort of source separation, and that's how you begin. Okay, so jumping on to the first one, This first one is vector quantized variational autoencoder based approach. A lot of people, I assume, might be familiar with it. And the approach is essentially a semi-supervised approach. It's not completely unsupervised. So you take this noise, you start with some paired speech and noisy and speech pairs. So you start with speech and noise. You create this paired version as usually you do in a typical speech enhancement training. Then you try to learn some discrete representations through VQAE, and then once you have done that, then you go to the next step where you use this pre-trained discrete representations to create unsupervised loss functions. And these unsupervised loss functions do not depend on the target clean speech. You can create them just by even for the noisy speech, and then you can train the network. So training the VQAE, like I said, you do it on the pair data. Basically, the process is same as before. Noise, clean speech, noise, you mix them to create noisy speech. You have the target, and you have all the references available. The main difference here is that what we are trying to do here is to learn speech and noise codebook. So the quantization in the codebook space for the VQAE, we separate the speech and the noise codebook, and then decode them, use them separately to decode both the speech estimate and the noise estimate and the noisy speech estimate. So overall, we do 3 estimations. So in a way, like this is what the source separation model I was talking about. We're trying to separate speech and the noise, and then everything else remains same as in any typical VQAE training. And the idea is to learn those speech and noise codebook or discrete representations. And once we have done that, once we have used this paired data or this supervised data, if I can say so, then we want to use the unlabeled data or just the noisy speech to train our enhancement model. So for that, if you have the noisy speech as input, then you have your speech enhancement training network, you get some output from it, and then you pass the output to the pre-trained VQAE. You get your quantized code books, and then you formulate essentially two loss function. Both of them can be used standalone, but one of them is essentially a triplet loss in the quantized domain, where the main idea is that we want the encoder output from the the encoder embedding to be closer to the clean speech than it is from the noise codebook. That's the LE. So that's an embedding in the that's a loss in the embedding space. And the same loss, the same idea could also be translated to the actual output space, where you try to make basically the enhanced speech closer to the clean speech codebook using the clean speech output estimate, and then from the noise estimate. So you have FS and FN as the estimated output from the decoder, basically the VQAE, and the loss function essentially is trying to put the speech enhancement output closer to the FS rather than FN, with some margin, which is a typical speech enhancement. This approach kind of works, somewhat works. We tried it on like this popular DNS challenge data set, and we used actually, and then we also, for the unpaired speech data, we actually took it from the wild, this big audio set data set. And depending on how you train it, you could be training on both the paired data and unpaired data. Overall, what we saw is that there are a few things which is really necessary. One is that you require a minimum amount of supervised data for the VQAE to learn something, and to learn something which is actually useful. And for that, we saw that if it doesn't happen until you use like almost 30% of the supervised data. And once you have, or actually, sorry, around 15 or 20%. Because if you look at the first one, the 10% one, the baseline approach, which is just the supervised training, is doing better than the unsupervised ones. Once you have learned, you increase the amount of supervised data available, then the VQAE is actually able to learn useful representations, and then the approach starts to give some improvement. Same thing we have seen in both seen noise conditions and unseen noise conditions. Yeah, so that's like the high level thing we observed. We have some more interesting results and analysis in the paper, but I'll skip that. To summarize basically this part, if you have some amount of pair data, you can use it to learn some representations, and you can formulate the unsupervised learning part through those representations. So essentially, you can create a loss function based on those learned representations. But a major point to note is that in what we notice is that this is not a very strong supervision. So and that's why the improvements we were getting was also relatively on the smaller side. But what we did notice was that using source separation as a formulation, basically, instead of the typical enhancement process where you just try to estimate the noise, the clean speech, formulating it as a source separation task, it can be very useful because now you don't have a target. So you can formulate it as like trying to separate noise and clean speech, and that could that could be a useful approach, which is what we'll use in the next approach as well. So the next work is called Remix It. And before I go there, let me see how I'm doing on the time wise. Okay, so yeah, I want to quickly introduce two things, topics which is related to it, and which are basically inspired Remix It. The first is my own work, which is called sequential self-teaching. So we did this work for actually improving generalization under noisy label conditions. So if you're learning from noisy labels, what we found is that the typical learning process is the one-step learning, where you take a data set, you train a model, and you get your model. This is just basically a one-step process. What we noticed, what our main idea there was that instead of that, if you're learning under noisy label condition, learn sequentially over multiple stages. So you do the first stage of learning, you have a model, then you use this model to guide the next stage of learning, and so on. So you can keep doing it until basically the model, you can't do better. And this could be this sequential learning. So that's the basic idea. So this could be done, how you apply it, that could be done in a variety of ways. We had a very simple approach where we take the teacher output and basically do a convex combination or a simple combination of the actual target space and the teacher output, and we train the network with that. That turns out to be really well, and at least on on this large scale audio set data set, it ends up giving a significant performance boost, achieving state of the art results at that time. But I won't that's not the focus for today. The other topic which I wanted to just quickly touch upon, because it is again related to Remix It, is this mixture invariant training. So this was introduced by I think by work from people at Google, where they introduced the idea of using mixture of mixtures to learn source separation. So the basic idea in source separation, also similar to speech enhancement, you would require the supervised, basically the target labels for each sources. What is the target sound sources? That's what the typical process. So they introduced this idea of learning from mixture of mixtures. So you have two mixtures, you mix them, and then you have your separation model, and then and then your output space consists of all of the separated sources. So you up to a max n. So here, for example, you assume that at max it can have like 3 sources, each mixture can have. So you end up with a total of 6 output spaces or output slots, and you try to fill all of them. Some of them can be empty. And then what you do is you take these outputs, remix them again, and then compute, and then create another output mixtures. And then your loss is basically between the input original mixture and this remixed or basically reproduced mixtures. And that's how learning happens. To make it more specific or contextualize it further, you can use it even for enhancement. And the way to do it is, and which can lead to the first form of unsupervised speech enhancement is, you start with noisy speech, the first one here, over there. and you mix it with noise, you have your separation network, and you try to estimate speech and the two noise sources. And then you compute a loss function based on the permutation between which one of them. So the first slot is fixed to be S1, but the second one could be N1 or N2. So you basically just take a permutation of between the two. That's a very typical source separation learning process. So now this gives us a first way to work up to think about, essentially unsupervised speech enhancement. The good thing is that it can use noisy speech, but still it requires standalone noises. So you need to have in-domain noises if you really want to learn. And it also makes assumptions that noise sources are independent from each other and they can be separated, which can be tricky sometimes. Now coming back to our remixed model, it basically is inspired from the sequential self-teaching and the mixed process. And in this work, what we essentially kind of combined the two idea and made it work for speech enhancement and learning from where we could learn from noisy speech directly. So let me break it down step by step. So we start with a teacher. So we have this teacher which is trained somehow. It could be trained on a small amount of supervised label data. It could be trained of using, say, the mixed approach, which is kind of unsupervised, anything. So we start with a trained teacher. Then we have these noisy mixtures, and that's all we have. There's no other either clean speech or no other noise available. We use this pre-trained teacher to get outputs from the teacher, which is an estimate of the clean speech and estimate of the noise. Now what we do is we take the teacher's estimate, and then we permute essentially all the noise estimate within the mini batch, for example. And we create a new version of, or basically a remixed version of mixtures. So now for a given speech sample, you can have multiple bootstrapped mixtures, where these bootstraps have been created by using the teacher's estimate and the permuted versions of the teacher's noise estimates. So that gives you some bootstrapped mixtures. And this is what you use for the actual student training. So for the student training, these bootstrap mixtures are the input, and the output obviously is trying to estimate the clean speech and the noise, and the loss function, which is L-remixed defined over there, is computed using the teacher's estimate and the teacher's noise and speech estimate. And so that's basically the teacher-student training part. And the continual learning part here is that there is your teacher is continuously updated, and there could be a variety of ways to do it. You can update it after, say, every X epochs, or it could be like an exponential mean averaging, or it could be anything else. But the idea is that the teacher should also continuously improve, just like I was talking about in the sequential self-teaching, that the teacher is also changing. So yeah, so this is the overall idea behind remixed. Take noisy speech, start with a pre-trained teacher, take noisy speech, get an estimate from the current teacher, remix them by permuting the mixtures to create bootstrap mixtures, and then use that to train the student. Yeah, so this is what this equation is basically showing. You have the loss between the student estimates and the teacher estimate for the speech, and obviously then a loss between for the noise. Again, this is a source separation. We are training it explicitly as a source separation model, and permuted versions of the teacher's estimate. So the main question is, how does the student learn to improve? Why will it do that? And we have some theoretical results, which is also supplemented by empirical results in the paper. And what we basically argue that both bootstrap remixing, basically this permutation and then remixing, both that, as well as continual refinement of the teacher, basically updating the teacher, they are both pretty important. And under certain conditions, and like Euclidean laws and so on, and then the number of bootstrap mixtures going to infinity and all, under certain conditions, we can show that the remixed loss can essentially be, like converged to a supervised loss. So assume that for that noisy mixture which we had here, this one here on the this one here, imagine that if this we don't know this S and N. So if S and N were known, then under certain condition we can argue that the remixing loss which we have through the through the teacher based estimate is almost equivalent to knowing the S and N and computing a loss using that. I'll skip that detail and jump into some results. Just an overview of some of the dataset names you will see probably in the upcoming slides. DNS challenge, that's a very popular dataset for speech enhancement. Then there is you'll see Libri FSD50K, which combines Libri speech. That's a large speech corpus with this FSD50K noise corpus. WAM dataset, which combines the Wall Street Journal mix dataset with again sounds, some 10 urban sounds, and then VCTK. A few things about the whole training process. Teacher can be any model. We use this model called pseudo RF architecture. I don't need to go into the details. The basic main thing is that you'll see a number. You'll see now parameter U, and the parameter U basically tells you how they're like. It specifies the number of blocks, certain blocks which we use, and the larger, the more. That means higher capacity model. Updating the teacher, you can keep it static, and like I said, or it needs to be sequentially updated. And there are a variety of ways you can do it after every k epochs, exponential mean average. Most of the experiments is done through this sequential update, basically updating after every 20 epochs or so. Learning conditions, if your teacher was initially trained in a supervised way, then it becomes again a semi-supervised approach, of course, because you started with paired data and then now we are using this unpaired data of noisy speech. If the initial teacher was trained using, say, a mixit, which I showed earlier, there you don't have the clean speech as target, then it's kind of more unsupervised, because now you have your initial teacher itself never saw, like clean speech target. So then it becomes essentially fully unsupervised. Okay, so let's look at the first set of results. Why do we need to update the teacher? So I'll try to show some results which basically argues for that. So if you can see here, the black and the gray dotted lines are basically cases where the teacher is kept static. The gray is one for U equal to 8 student, and the black is the one for U equal to 16. And if you keep them, you get some improvement, and the teacher is updated after every 20 epochs, and that's the one with the orange line. So in that one, you can see that if with the sequential updating, you can actually continue to gain improvement. Now, one may argue that maybe it's just because the student capacity is increasing, so we are seeing better performance. That's not actually the case. So if you compare the black one and the orange one at epoch 40, they are both basically same capacity student models, so U equal to 16, but with sequential updates. The orange one, where the training was done through sequential updates, you see a better performance, which basically means that even if you want to, the sequential updating can actually give you an improvement in performance, even for the same capacity model. So it can lead to better, faster convergence and better results quicker. Overall results, this is a pretty big table, so I will discuss just, I want to highlight just one thing here perhaps, and that is that compared to the full so if we compare, of course, like if you have supervised in-domain training, where you have the actual large-scale supervised in-domain clean speech and noise samples available, reaching that performance is still it's still difficult. But if you but compared to another unsupervised approach, say for example mixate or something, we can get almost like 1.5 dB or 0.3 in PES improvement, which is a pretty significant improvement. That's one thing I wanted to highlight. And second thing is that in the and this is all using out of domain mixtures. So we never use in domain clean speech samples or noise samples. This is all done by using unsupervised. This is all done through out of domain mixtures. Anyway, there's a lot of information in this table, but let's jump to something more interesting. So what about the progression in learning? So how does that how does the student learn? So to do that, what we did was we tried to look into different type of teachers. So what you see here is each plot is basically for a different teacher whose outputs lie in different range. So the first one is like where the outputs are pretty bad. So like -30 to -20 dB SNR. So these are pretty bad teachers, and the one on the extreme right is basically pretty good teachers. So what you will see is that there are few things to basically notice. The first one is that if the teacher is really bad, there's not much you can do. The model is never able to recover. So, and the x-axis is basically showing the training epochs. So you can see that on an average, basically the model stays. You will get some delta improvement through this basically knowledge distillation. That's why it's above 0, that the delta is bigger than 0, but you are never able to recover. You stay where you are. Whatever basically the student has, the teacher can do, that's where it stays. Whereas for the really good teachers, even though now we are talking about pretty good teachers where the output is already really good, we can still see that the trend is kind of upward. You can still see some improvement in the output. So that's this also matches with a theoretical result we showed in the paper that if the teacher learns to refine itself, then the loss is able to go towards the supervised loss. Okay, moving on. So what can we we do about bad teachers? So if the teacher is really bad, it's hard to recover from that, and probably we need some a different mechanism, or we need to that's like an open problem. But if the teacher, but for not really bad teacher, but somewhat bad teacher, we try to see what can impact the performance of the student learning. So the plot here is showing basically the distribution of SNR improvement over the initial teacher after just 10 training epochs. So we are looking at a snapshot at the 10th epoch, and we vary the number of bootstrap mixtures. So the number of mixtures which you create, that varies from 1, 2, 4, 8, 16, 32, and 64. So we vary that and see how the student learns. Is the student able to learn better if we have more bootstrap mixtures? And that's exactly what we see. That on an average, if you increase the number of bootstrap mixtures, the student is able to learn more and more. So for any given speech sample estimate, you'd like to create more and more augmented versions of it to train the student. And that can help somewhat recover from, so even after just 10 epochs, the last plot, if you see b equal to 64, the student starts to do pretty well. So that could be one way to recover from really bad teacher. And obviously after that, after you have done some iteration of learning, you refine your teacher. So basically now your teacher will become better. Like I showed in the previous slide, if the teacher becomes better, the student will still continues to learn. So that could be one way to recover from a bad teacher. Okay, so some more stuff from Remixit, which is shown in the paper. We can adapt to test time. So basically, if you have some test samples and you're not bothered by anything real time, and you have just to do offline, say, speech enhancement, you can take you apply this approach and actually do test time adaptation and get good performance. We also showed some generalization across all different versions of the data set, which I showed, and cross domain, and in most cases we are able to, we can actually do pretty good generalization. To summarize, what I discussed was an approach to utilize and adapt any given model through just noisy speech mixtures without using any clean target. And the main thing to remember is that both sequential learning, basically this teacher continual learning, as well as remixing or bootstrap remixing are important. Okay, so let me see how fast I want to go then for the next part. Okay, I have some 10 minutes. The story so far, we looked into speech enhancement, basically where we were talking about improving quality and intelligibility, and in particular, unsupervised speech enhancement, where how can we learn from noisy speech mixtures. Now, the other part of the talk is about speech assessment, where we are talking about how to measure quality and intelligibility in the first place. And in particular, I'll be talking about non-intrusive method for speech enhancement, and I'll go over what I mean by that. So before that, what is speech enhancement and why do we need it? So speech enhancement, basically assessment is basically how good or bad your speech signal. If you are hearing something, is it noisy? Are there some sort of distortions? Are there the artifacts? Can you rate, if you rate them between 1 to 5, how good or bad it is? That's what a speech assessment is basically. And it's basically required for essentially any audio and speech technology you want, whether it's for hearing aids, communication, enhancement, separation, whatever. If you're working on speech, you probably need a way to measure how good or bad your speech signal is. It's also obviously critical for development and iteration of speech models. Like if, say, for example, you're working on enhancement, then you need to know, you need to not only know that how good or bad your current model is, but that information can be used to actually improve the next iteration of the model. So so the gold standard process for speech assessment is obviously evaluation by humans. You people here, oftentimes you may require some expert listeners, and then they'll provide you a rating of some sort. Like a popular one is called mean opinion score, where you provide a rating between 0 and 5 to the speech signal, like whether how good, depending on how good or bad it is. If it's really good, then maybe a 5. If it's somewhat good, then maybe 1 or 2. Obviously, this is very time consuming. It requires a lot of effort actually setting this up. You want to make sure that the environment there in which the listeners are is same. You want to make sure that the equipments they use, like it's same. So it requires a lot of effort to do these subjective evaluation, which is obviously infeasible in a lot of times. So people have come up with these objective metrics. What are these objective metrics? These objective metrics basically compare your given signal to the known reference signal. So you have the degraded version of the signal, as well as you have the reference signal, which is the clean signal. And then based on what you really want to capture, over the last 2-3 decades, a bunch of objective metrics have been proposed, like PES, Polka for quality, STOI for intelligibility, VISQL for quality. There are a whole bunch of them. I'm not mentioning all of them, but the basic idea is that compare your degraded signal to the reference signal and come up with a number which tells you how good or bad the signal is. What are we trying to do here? So recently, especially with neural networks, people have started looking into speech assessment using neural networks. And in particular, what we are trying to do is to make it non-intrusive, which basically means that it should not require that reference signal. So this here, all the objective metrics needs this reference signal. We don't want to use it. And why don't we want to use it? Because in real world, you don't have that reference signal. So if you collect a speech sample from the real world, it will have some noise, it will have some degradation, it can have some artifacts, but you don't have the clean reference. So how do you measure, how do you assess that without using obviously human evaluators? So we want the model or the system to be non-intrusive. For more scalability, we want the system such that it can estimate multiple metrics at the same time. It can run on scale. Another desirable characteristic is that for the neural network-based speech enhancement is that they are differentiable. So since they are differentiable, they can be integrated with any neural network or any other system, and you can basically use them to improve your current say speech enhancement model or ASR model or anything else. So that differentiability is also helpful. So these are the reasons to look into neural network-based speech assessment. Again, recently, last at least 2-3 years, there's a lot of work doing this. And here's a basic idea behind doing it. We have a data set. In the data set, you have distorted speech, reference speech, and you compute the metric between them. You take your neural network and you ask it to basically learn to predict whatever metric you want. Say, for example, pest, toy, or whatever you really want. There are two ways to usually do it. The one in which the network requires both distorted speech and the reference speech as inputs. So there is some grounding happening, just like any other objective metric computation. And there is another one which is the non-intrusive one, where the input is just the distorted speech and the network learns to predict the metric directly. So if nothing else, I would like to highlight this part here. Most of you are probably familiar with PyTorch, and within PyTorch, if you're working on audio speech, you likely are aware of Torch Audio. It's basically the equivalent of the Torch Vision or Torch Text, I think it's called. It basically provides everything, base fundamental modules for audio processing and speech processing in PyTorch. And within that Torch Audio library, we are releasing what we are calling Torch Audio Swim, which is basically speech quality and intelligibility metric modules. And that will allow you to estimate subjective as well as objective metric in a non-intrusive way. And the current version will be out probably in a week. I think the objective one is already out. Right now it's in the it's not in the stable release, it's in the, so you may have to use the nightly built version. But eventually it will be moved to the stable release as well of Torch Audio and PyTorch. Using it is fairly straightforward. It's literally like 2 lines of code. You import the model and just run the model, and that's it. Performance-wise, we have a paper in ICAS where we showed that it does fairly well in PESC estimation. The error is less than in general 0.14, 0.142 on an average. For a SISTR estimation, it's usually less than 1 dB. And similarly for the MOS estimation, or mean opinion score estimation, which basically is the subjective evaluation. So here the model is actually trained on MOS data set. For that also we are releasing a model. The one thing I probably want to note, which is also what I'm going to talk next, is that in this case you will see that the model is actually using the test waveform and something called a non-matching reference. So it relies on grounding using non-matching reference. So what really is that? So I'll end up by talking a bit about non-matching reference-based speech quality assessment. So here the main idea is that we saw earlier that either you use humans and who to do evaluation, who often are also, by the way, trained to understand what is the reference speech. So what is the speech which is like a rating of 5? So you often need the listeners to you often need to train the listeners to understand that. So in general, people, you need basically some sort of grounding. Whether it's the objective metric or the subjective metric, you need some sort of grounding for any model, whether it's human or a neural network or some computational model, to understand what is the degraded signal, what is the worst degraded signal, what is the best undegraded signal, and so on. So now when we talk about these non-intrusive methods, now the model has no grounded at all. The input is just the degraded speech. So how do we learn to can we do something about that? Can we provide it some grounding? And that's where the idea of learning with non-matching reference comes from. So what's the main intuition is that humans can compare quality of non-matching signals. So I don't speak French, but if I hear a degraded French speech signal and another one in, say, English, I can still say that which one is cleaner, which one has more noise, which one has more artifacts, even though I don't understand the content of the French speech. So intuitively we can compare. Now I do want to say that maybe people who work in auditory perception might have a slightly different view here, but intuitively to me it makes sense that you can compare even non-matching signals, different speakers, different language, and you can still say how do they compare with respect to quality and intelligibility. So, and the second, from the learning perspective, is that learning to compare might be easier than trying to directly predict an absolute rating. This is more about the learning dynamics. So if you have a given speech signal and some sort of grounding, that can lead to that can make the model learn easily and even better estimates. The good thing is that when you're using non-matching reference, so what non-matching reference is basically any reference where you know the quality. So it could be basically any speech signal in any language or any spoken by anyone. All you need to know is what is the quality of that signal. If you know that, then that's all you need. So it's still non-intrusive. It's not changing the behavior, and it's still of the model as far as intrusiveness is concerned, and you can still use it for real world speech signal, because for real world you can use basically any non-matching reference as long as you know the quality of the non-matching reference. So it retains basically the practical applicability of non-intrusive models. So just to illustrate what the main idea looks like. So you have a test signal, a no reference model would take this test signal and it will spit out some rating or a number for it. A full reference one will basically take the same speech signal, the clean version of it. As you can see, the test one is is missing some frequency, in the signal. So you need the exact same speech spoken by the same speaker, basically the clean reference for it, and then it will take those two and predict some rating. What we are saying is that it is basically something which you can say is in between those two. You provide some grounding by adding a reference which is not the actual matching reference, but any other speech signal, and pass that to the model along with the test signal, and then you can compute, and the rating is computed based on and the learning happens through this grounding. So the first idea we introduced was to actually we had a new Rips paper in 2021. We showed that this is actually doable, and providing grounding through non-matching references is actually can actually lead to better model. I won't go into I think running out of time into how the whole training framework works. You can check out the paper for that. But to show some results, a popular non-intrusive MOS estimation model is from Microsoft. It's called DNS-MOS, where they trained a neural network basically on a very large-scale MOS dataset. Our model, based on this Noresca framework, was trained using actually a very tiny MOS dataset. It's like much smaller, like an two order of magnitude smaller than what was probably used by Microsoft. And we show that that can outperform DNS-MOS on a diverse set of 15 different data sets and tasks. And most of them, depending on which metric you go, it outperforms DNS-MOS on 10 or 15 or 14 of the data sets. And here is a visualization of it. So if you see, the x-axis here is the actual MOS, the y-axis here is the prediction by the model, the one by DNS-MOS, and then NMOS is basically our model. And the closer it is, the more aligned it is along obviously the y equal to x-axis, the better the model. And we do much better. DNS-MOS suffers from this problem that it's very biased because of probably of the data set it used. So it always predicts a number which is greater than 2. Another thing, one problem with our model is that right now in the current form, it saturates very often. So oftentimes it will predict the highest, above 4 kind of rating. And we are looking into solving that problem. You can see that there's a line, almost line like that, and the model often makes that mistake of predicting a very high MOS. So there is some sort of bias there in our model too. All right, overall, I'll summarize. I was talking about self-supervised or unsupervised learning for speech enhancement. It's a really interesting problem, I think, learning from without target speech. We try to do it through both by learning some representations, and then also directly in the audio space through continual learning and bootstrap remixing. On the speech assessment side, the main part I wanted to highlight was this idea of using non-matching references for speech quality. And lastly, this Torch Audio Squint tool, which we are releasing in Torch Audio Library. And we are looking for people to use it and give us some feedback where the model currently fails, where it works well. So yeah, that's it. And thank you everyone for listening.
Thank you, Dr. Kumar, for the talk. So any questions from the inference audience?
Yeah, I have a couple of questions. So first of all, thanks for the talk. It's excellent. I like your reference-free speech enhancement. The self-supervised learning is definitely more scalable than requirements of clean audio. So now, from your understanding of this large-scale self-supervised speech enhancement, what is the key limitation? Right? Is it in the lack of proper data, or is it in the lack of a strong enough neural network model, or this is because the lack of better loss functions, or the tasks that you formulate? Like here, you formulate different kind of tasks and different supervision signals. What are key limitations, or all of them are still limited?
Yeah, probably all of them are still limitation. What I feel is that one way it's different, like self-supervised learning model, a lot of them have been, if you see like the most popular ones, mostly they are tailored towards, they will either do some sort of contrastive learning or, predictive coding type of formulation. And they're very much geared towards classification tasks. So they do work really well in classification. So even for speech, when speech SSL models, when you use it for say ASR or such task, which is basically a classification task, they do well. I mean, you can, with even a very small amount of fine-tuning data, you can get a pretty good ASR model going on. So, but the main difference here is this is about the type of task we are talking about. This is here where an audio is generated, and that audio is generated and it's more for perceptual consumption rather than a classification task. So in classification, an output changing from say 0.8 to 0.7 doesn't change your classification label. But the same thing, something happening like that in the generated one, it will change. And especially for audio, it's much more important because you can, that will really change how the frequency component of the model, of the output, basically the frequency characteristic of the output, and which would internally change, which will basically mean you will hear something else, you will hear an artifact. So it's very easy to get artifacts and distortions in this model. Especially for so that's one big problem. Another problem is that, which is basically about the task itself, is kind of different. So you need probably a different type of formulation that could be in a different type of supervision and loss. But if you don't have the target clean speech, that becomes very tricky to actually formulate that. So a better one could probably lead to better results. Another major point perhaps is that most of these SSL model, they're trained on basically clean speech, at least on the speech side. Noise is not a factor there. So learning robust representations with noise, with noisy speech, is challenging on its own. So you can learn good phonetic representation of using clean speech. So all speech SSL model, they're learning some or the other form of phonetic distribution. And that's easy to do if you have clean speech, or relatively easy to do. But if your input itself is noisy, and the noise could be like at -10 dB SNR, we humans can't hear a lot, right? So, and we can't understand a lot of it. So learning robust kind of, like speech and noise distributions when under such high noise conditions is also very difficult. So that's another reason it makes the problem even more challenging, because we want to also focus on how, because the task of enhancement by definition is about taking in noisy speech and producing something better than that, right? So if you don't know how to learn well from that noisy input, it's hard to get any like any improvement, especially when you don't have the target label, target clean speech. So yeah, the solutions could be better loss functions, some other form of supervision, maybe adding maybe an audio visual one could be more useful, especially in the noisy, very high noise condition. Maybe that could lead to better representation learning. Yeah, but I think that's still kind of open on what's the best.
Okay. Yeah, on a related note, do you think speech enhancement can be solved by its own, or intuitively, I feel that if I can understand the semantics, that in turn also helps me to do speech separation or speech comprehension. Do you think it should be connected with some speech to language comprehension model, and to help each other?
Yeah, that's a great point. So in general, yes, knowing the semantics, the language, and definitely helps us improve even things like spatial characteristic of the speech signal. That actually improves the intelligibility. If you know where the signal is coming from, at least humans can have better intelligibility. People have shown that. But the problem is that, and there are some work which have tried to use text and all that as input to provide that, like linguistic information. But the problem is that our main focus is, like on this real-time use case, where we are using speech enhancement to almost in real time, less than 20 milliseconds. So in that case, in real world, you don't have this semantic or the linguistic information available, or it's not easy to inject that information. Like if I'm just talking to you in a noisy, say, restaurant, I mean, like injecting any sort of linguistic information prior is not that easy. It's possible, but it's not that easy.
What if we just use it in training?
Yeah, so this is what these solutions are going towards, like somehow using. So I did not go into the details of my using pre-trained SSL representations. That's what we try to do there. Use the SSL representations only during training. Don't use it during inference. That SSL could be also a visual signal. That SSL representation could also be a text representation. But yeah, so far I have not seen any like work which have like shown convincingly that inference time, training time only uses of this additional modality has worked out that well for speech enhancement itself. But yeah, that is the approach which probably we need to go.
Thank you.
So any more questions in this room?
I guess I was going to ask something similar. In thinking about this speech enhancement with a full headset, you have so many more data streams to kind of draw from. Are you working on developing models that include, just like with wearing masks, it's harder to decipher speech when you can't look at someone's mouth.
Yeah.
And so even a little bit more visual information.
Yes.
And the other question I was going to have was, I don't know much about these models, but do they label speakers? Can you label an individual speakers by voice or something and then track that signal in the data?
Yeah, good. Yeah, great points. Yes.
Like if you're sitting having a conversation at a table.
Yeah, we are actively looking into it. So we have actually quite a few papers on audio-visual speech enhancement and separation. So we are looking into how to use the visual information in particular, especially, and they become very critical under high noise condition. So when the noise is kind of on the not that high, like above say 5 dB or so, current state of the arts audio only model does fairly well.
What's like a 5 dB example? I don't have a good match.
Okay, I don't like a bit.
A noisy bar.
No, that can get very loud, and noisy bar would be like, I don't know, -10, -20, depending on the noise in the bar. It can go pretty crazy. This would be more like you have a bunch of people in the house, and maybe they're sitting in the living room. You are in the kitchen, which is just a few feet away. There's still a lot of like some music, something going on.
Like
so some noise
together.
Yeah.
Okay.
Yeah. So Yeah, so they do well, but under high noise condition, visuals become very important. So we are looking into it. We actually even have a paper out right now where, again, the problem with using visuals is that we have to processing visual signal becomes more computationally expensive. So if you're looking into real time and all that, there are more problems to solve, like compressing the model, making everything in real time. Yeah. So that's one challenge there. But yeah, that is something about the point about speakers, using speakers and kind of speaker information. Yes, we don't have a paper out, but that's also, we are actually looking into it, that how can, if you know the person and how they speak and like their specific speaker characteristic, that might help remove some of the distortions and kind of a personalized.
Yeah, I would imagine if I was developing a speech enhancement model for me personally,
yes,
I would have a library of my top 10 speakers who would have a vocal profile that could be matched.
So there's a challenge, the DNS challenge dataset, which I was mentioning. As part of the challenge, there is also personalized speech enhancement is one of the challenges there. And at least in last 1-2 years, if few works have come out on it, and we are also actively looking into it.
Yeah. The other question I had was how much interplay do you have with the hardware? Are you building speech models depending on like distance of microphones and speech localization and sound localization? Do you go back and forth with in your work with people doing the hardware development and maybe people who are audiologists and neuroscience? How integrated is the whole development process?
Yes, you're hitting the right points. So yes, that is the overall process. Most of what I talked about here was single channel and very much kind of a deep learning driven approach. But our team, yes, we have audiologists and people who are more from auditory perception and hearing science expertise. And yeah, we do work with them. And like eventually the whole model will be all those steps, working with audiologists and, people with auditory perception. So yeah, that is going on. But I think this speech quality thing, which I mentioned, is kind of a surrogate way to do it because it provides you some sort of a rating or evaluation. It's obviously not precise, but if you can have that, maybe that can be used to improve the speech enhancement. On the part about localization and all that, yes, that requires, this work was, the whole discussion was on single channel. We have quite a lot of work on multi-channel. So when you have more than one microphone, like 6, 8 or whatever, then yes, you can localize where the sound is coming from. You can do beamforming and things like that, and that can further improve the enhancement. So yes, we have actually quite a few papers on that. We are also, just to add that, looking into not just producing single channel output, but actually binaural output, so that when you are talking in real time, the spatial characteristic of audio is important. So you don't want to lose that. So otherwise you lose the the sense of communication and immersiveness, right? So we are also looking into doing enhancement, separation, and all these tasks in a binaural way, so that we retain the spatial characteristic.
My last question, sorry, do you do like machine learning or categorization or labeling of typical real world noise environments?
Yes. So that's
like, okay, this is speech enhancement, but it's in the context of like a noisy restaurant. There's going to be clanging, and so now our speech model can recognize a clang and kind of damp it down or something.
So that's actually one of my other area of main area I work on, like sound events understanding. So what type of sounds are happening in the event, which scene you are. So yeah, we are very actively working on it. And combining that with enhancement, it's we have looked a bit into it. I don't think we have any paper publicly out, but the results are kind of mixed. It's not. It's mostly mixed because the current state of the art for speech enhancement audio only is fairly good for in-domain noises. So if you know the context, so for in-domain noises. So if you know the context, So if you know the context, like these are the type of noises I want to handle, then with these neural networks, you can get really good performance.
It really makes a difference, like kind of knowing what noises to expect and stuff.
Yes. So But if trying to generalize is the question, it's like detecting the scene, classifying the scene, putting that information. It does give some improvement, but yeah, but not ideally. We want it to generalize in a, like not very contextual dependent, but actually something which generalizes everywhere. But yeah, using that information is something we have looked into.
That's excellent.
Thank you.
Any more questions? And I didn't see any questions posted in the chat. I think with that we can safely conclude this talk.
All right.
And, could you unmute on the way?
All right. Thank you, Dr. Kumar, for joining us. Can we just unplug? All right. Okay. Thank you, Dr. Kumar, for joining us today. We're very grateful to have learned about your work. Thank you also for everyone who attended, both in person and online. If you would like to continue following Dr. Kumar's work, please follow him on LinkedIn, and the info is posted in the chat. And please also check out our last Voices of XR series event in the coming week. Q. Harrison Terry will join us on Friday, April 7th, and we'll discuss his book on the Metaverse Handbook. And the link is also available in the chat. And thank you all, and have a wonderful day.